Hi there, my name is Amy McLuckie and these are my presentations for EDTE2520 for the scientific investigations. First investigation is the living world, where I've done early stage 1 and we're investigating what happens to the leaves of celery stem when we change the colour of the water. Or you could do this with petals of the flower changing colour when they change in the water too. And the prediction is that they will change to match the colour of the water. Here's the ingredients that you need: celery, food colouring, cups, something to measure the water and the food colouring, a knife and a chopping board and a ruler. The method is to set up the 4 cups in a line, add the same amount of water, 1/4 cup to each cup, and then add the same amount of food colouring to 3 of the cups. And no food colouring in cup 1, 15 mils of red in cup 2, 15 of blue in cup 3, 10 red and 5 blue to make purple in cup 4. Select 4 stems of celery with a similar amount of leaves, line them up and cut them to an equal length, 20 centimetres with a sharp knife, and then place the stem in each of the 4 cups, taking note of the time, and take a photo of the celery every 20 minutes until 1 hour, and then again after 12 hours. Here's a picture of setting up the processes. And here is the results table where we are recording what we have seen with the celery. So there is also some photos to show that over time the colour in the leaves where there was food colouring in the water increased. So here's at first setup at 0 minutes, nothing in the leaves. Here's after 20 minutes, there's a slight colour change in the red, less visible in the blue, and also only slight in the purple. A little bit more after 40 minutes, and after 60 minutes there's a noticeable colour change in the leaves. And here is a video.
This is our celery experiment after 1 hour of time in the water and coloured water. We've got the control there without any colouring, the red, the blue and the purple, all showing a change in colour of the leaf depending on the colour they were sitting in.
Okay, and here's some comparative results from when it first started to after 1 hour. And here's a photo of the celery after 12 hours, showing that it's drawn quite a lot of that water up and the leaves are nice and coloured there. So the conclusion is that the water moves up the celery and into the leaves, and as it does so, the colour of the water that the celery is sitting in changes the colour of the leaves to a similar colour. So the class is provided with a testable question and they can have an opportunity to make a prediction. They can then plan and conduct the test using fair testing. So the independent variable is the colour of the water. The dependent variable is the change in the colour of the leaves, which can be observed using photography and colouring in pictures for the kids, and keeping everything else the same is our control variable. So same cups, same amount of water, same amount of food colouring, same length of celery and same amount of time. This experiment should be done in groups, in classes. That way you will have a nice repetition of the experiment to replicate the data, and the photos help to measure accurately. Students can then communicate what they have found with their results and whether it happened the way they thought it was. And then as a class, they can be conclusions made about the experiment. So these are the strands outcomes addressed. And this is a design and production extension where you can try to design colourful flowers for someone who's only able to get white flowers using that knowledge. And the concept is about transpiration of the plants absorbing water and moving up through the plants, and that plants need water to survive, so the needs of living things. Okay, so the next presentation is Earth and Space. And for this one, we've done some sand dune modelling for stage, for stage 2. So we'll just get that up. Okay, so Earth and Space Stage 2 is the next investigation, and the question is, how are sand dunes formed, and to model the process and the explanation. Turning this into a testable question: what happens to the movement and shape of sand when the wind is applied from different angles and with different items on the surface of the sand? Predicting that the sand will be carried by the wind, moving in the direction of the wind until it meets an obstacle and then begins to form a mound or a pile of sand, forming a sand dune, and that when something is on the sand, that the mound will be higher. This could be extended by testing many other variables, incorporating different elements that might be relevant in real life situations. So you can do a longer period of time that the wind's blown, different objects, vary the wind direction, different wind speeds, adding water, so to simulate wave action, many things. So what you need for this is a bag of sand. It has to be dry sand or it won't work. A large container and some cardboard to create a wind tunnel, minimise the mess, a hairdryer to create the wind, and a ruler to measure out your distances, permanent marker to mark them, and notepaper and pen. So spread the sand out in an even depth, starting a little bit higher and then gradually sloping backwards towards the back of the thing as per the depths indicated here in the table, and then set up all the cardboard around the outside and set up the hairdryer in a stand so that it will blow consistently from the same angle and point. Then you will set the wind / hairdryer for 5 minutes running, blowing wind from a regular distance, and then after this is done, record the depth of the sand at the 7 points where you had recorded them before starting the experiment, and compare the before and after of sand depth, showing us how much the sand has moved and where it has deposited. So you'll run this experiment with different variables to test different effects. So with nothing on the sand, when the hairdryer is flat, giving a flat wind or an angled wind. Repeating this with rocks on the surface, flat and angled down, and plants on the surface and flat and angled down, to determine the difference and what's most effective at catching the sand. Here's some videos of this happening. So we've got a flat and an angled wind with just the sand. You can see there is definitely movement of sand there. At the angled wind, the sand movement is quite dramatic and creates quite a steep dune straight up, and it's a little bit more subtle in the flat wind. Here we have with some rocks as obstacles. Again, getting some more immediate results with the angle, but still getting results of sand building up over the top of the rocks, creating a mound. Okay, and this next one is with plants, or a simulation of plants, and again with a flat wind and an angled wind. And after all of these, the depth at those 7 points that are marked on the cardboard is measured. They all start at the same depth. So here's the results table where we've filled in the depths of all of the sand after each experiment. And here's what it looks like on a graph. So the yellow is showing what the sand depth was before we started. So they're all the same, and it's a gradual slope down. And after the wind has been applied, you can see in both cases with an angle and with a flat wind, we are seeing an increase in sand. So these little hills are basically showing us what the shape of our dune looks like. And we're seeing that our dune is a little bit different depending on each of the different variables there. So we can conclude from this that as the sand was hit by the wind, it's carried along in the direction of the wind and eventually builds up as bits slow down and create an obstacle to create a sand dune. And that different shapes would be formed depending on the wind direction and what obstacles are there. The dunes, we noticed, were higher when there was a plant in the way, so this is better at catching the sand. So here you're modelling doing working scientifically skills by modelling how the sand dunes are formed. There's a testable question, and the class can be guided to develop this question and plan their experiment. So they can discuss factors that they think would affect the formation of sand dunes and then test these, so the wind directions and different obstacles. And they can do this from research and discussion. And the experiment allows to model this process in a measurable way. It's a fair test using an independent variable of the wind direction, flat or angled, and the object used to block the wind, rocks or plants. The dependent variable is the depth of the sand, and there are many controlled variables: the amount and depth of sand, the amount of time the wind is blown, the shape and the size of the container and the wind tunnel, and the position of the wind source. This can be repeated many times within the class by splitting the class into groups, and each group sets up their own test using a smaller model. And this gives them time to free play with the effects of the wind as well. And the teacher might need to help demonstrate how to measure the depth accurately, and then each group will present their findings. Here are the syllabus outcomes: working scientifically and content-based. The design and production extension could be to design a method to prevent sand being blown into the local park. So discussing a dune revegetation program and how they could create a sand barrier to create a natural fall dune where there has been clearing along the beach area. Okay, so that's the Earth and space. The next presentation is physical world. Physical world is the third investigation, and that is addressing stage 1. The prompt is: what happens to the pitch of a rubber band when plucked if we change the thickness or the amount of stretch of the band? Turned into a testable question: what happens to the pitch of a rubber band when plucked when we change how much it is stretched? Here's what you need. There's a board with some nails, hammer, ruler, pencil, and rubber bands. Draw mark out even distances between the nails and hammer the nails in, and then stretch the rubber bands a vertical distance that is increasing as you go along to increase the stretch of the band. Some of the children may need help stretching the final few bands as the stretch is quite difficult to reach. They can then pluck the bands to listen for the differences in sound that are created. Here is a video of the sound. So we can hear there that when the elastic bands were thicker down at the bottom end, not stretched as far, the sound was a lower sound. And when they were stretched so that they were quite thin, the elastic band made a higher sound when it was plucked. Okay, so the thinner you stretch the band, the higher the pitch of the sound. The sound that is made when the rubber band is plucked is created by the rubber band vibrating, and so the more stretched it is, the thinner the rubber band makes the rubber band vibrate more quickly and making a high-pitched sound. And here's the concept demonstrated with how sound vibrations work. The vibrating object moves the surrounding air in a sound wave, which reaches the ears. The stronger the vibration, the louder the sound, and the sound will change depending on how fast or slow the object is vibrating, and the pitch is to do with whether it is high or low, and this depends on the speed of the vibrations. The high-pitched sounds will have a higher frequency, more waves closer together, and lower-pitched sounds have a low frequency and the waves are further apart. Okay, so working scientifically, there's predictions about what sound might be made. There is experimentation with stretching the bands, and children can communicate, discussing in groups what they've found. It is a fair test. We have an independent variable, which is the distance the rubber band is stretched. The dependent variable is the type of sound produced, high or low pitch, and the controlled variable is the rubber band type, starting with a 1.5 mil rubber band. The method of stretching the rubber band using the nail and board. Here are our syllabus outcomes, describing common forms of energy and exploring characteristics of sound energy. And here's a design and production extension activity where the children can use their knowledge about how to make different high and low pitch sounds to create their own band with instruments made from recycled and sustainable materials, and need to be able to create instruments that can make a variety of different high and low pitch sounds. They can have some instruments that are stringed, which is replicating what they've just done, and then also using this knowledge to create other instruments that demonstrate the concept in a different way. Okay, final presentation is for the material world. For material world, the investigation prompt is what is the optimal ratio combination for vinegar and bicarb rockets? Turning this into a testable question, we can ask what happens to the amount of time taken to launch and the height of the launch when we change the ratio of the vinegar and bicarb in the rocket. So here's the equipment we need for the reactants. We have white vinegar, baking soda, aka bicarbonate of soda, or bicarb as we will refer to it now, some paper towel or tissue, some sticky tape, whiteboard marker, funnel, and measuring cups and spoons. We're also going to do a little pre-test with some of those reactants in a bowl and a tray. And creating a rocket for our actual experiment, we need 600ml plastic bottles, a rubber stopper that fit the bottle snugly, chopsticks or pencils or some kind of stick of equal length to create the stand, and duct tape or packing tape. And we're also going to need some things to record it with: camera, stopwatch, some measuring tape, launch site, tarp, and notepaper and pad. Okay, so to set up our experiment, we will begin by testing what happens to the ingredients when you combine them in a bowl. We're going to add the vinegar, about 1 cup to a bowl, and then 4 teaspoons of bicarb into a separate bowl. Each group can get this, and then they can pour the bicarb into the vinegar, ideally on a tray to minimise mess, and then combine the ingredients there. You can see the reaction occurring, picking up that bicarb, popping it in there. So we can see that straight away something is happening. We can see that a gas is being produced there because we're seeing lots of bubbles forming in the mixture. Then we're going to use this pre-test activity to predict what might happen when we do this inside a sealed bottle, and this will help guide the planning investigation. The students will then work together to plan the investigation using fair testing and to create predictions on what they think will be the most optimal effect. So to determine an answer to the question, we need to decide what it is that we think is optimal. So do we want it to, how high do we want it to go, and how quick do we want it to react? And they can then decide on how to vary the quantities of the reactants in the mixture. And we can see here we've created a table to record that data. So in one part of the experiment, we're keeping the bicarb stable at 4 and then changing the vinegar, reducing it by 1/4 of a cup each time from 1 down to 1/4, and then reversing that and keeping the vinegar stable at 1 and changing down the bicarb by 1 teaspoon at a time. You then need to create our rockets, attach the sticks or chopsticks or pencils at an even height to the upside down bottle and tape them on, and then make sure that rubber cork fits snugly. Creating the packets, this is to act as a time release. Without any packet, the reaction is too fast and you can't get the cork in. So this is quite a precise fold to make sure that it's consistent, because there is quite a bit of variability depending on how it is folded and what thickness of tissue or paper towel is used. So this is done with 1 ply of tissue, so separated out of tissue to 1 ply, cut it in half, and then popped the measured amount of bicarb, as you can see, making sure that we're measuring accurately so that we have the same amount of bicarb in each, folding it in the same way so that everything is the same. And then at the end, just put a tiny little bit of tape on there and label how many teaspoons of bicarb we have in that packet, and make up all the packets for the experiment in one go. We then need to set up our launch site. If you have some concrete, you could do it straight on the concrete, but on grass, it's good to put a tarp down to protect the grass, because the reactants, the products of the reaction can burn the grass. And then we have some little stable launch pads so that our bottles don't tip over, and has helped us to label which of our mixtures will be going on what part. Using surrounding landmarks to find out how we can measure the height and compare with our bottle launch, and then pour the amount of vinegar we need into each bottle. If you don't have surrounding landmarks, there might be a possibility of like developing this further to change the angle that the bottles launch at so that we could measure a horizontal distance rather than a vertical distance. But in this experiment, we've done a vertical distance using surrounding landmarks. Then the next step is to launch the rockets. So it's helpful to film this process to make sure that you can check back over your results. Carefully pop the bicarb packets into the rocket, seal it up straight away with a rubber cork, and turn it down and set it. Then move on through the rest. Ideally, you could do this all at once with a group of children. The timer should start as soon as the cork has gone in and the rocket has been tipped and set, and started and stopped at the same time for every rocket. Record also the highest point that the rocket launched, and then wash down the launch site and reset again, and repeat this test 3 times for each variable as according to our table. After this, we will then analyse the results, graph them, and discuss the data and the trends, and then the groups can report back on their conclusions to the class. So some of the rockets have gone really, really high. The very last rocket that goes off here goes up over the roof and hits the roof and then comes back off again. So it's quite fun to do. Here's our results table. So we've popped in the time that it's taken for the actual reaction to launch the rocket, and then how high it's gone. And the height, in order to allow us to graph that easily, is put into levels. So there's a range of meters that the rockets reach to, and then the level that that is. To create the average, which is what the graphs are made from, we have just added up the 3 test results and divided by 3, and for the height level, to make sure that it stays on the 1 level category, we've just adjusted to the nearest whole number. So here's our graphs. This is with our vinegar as the variable, so we've got a stable 4 teaspoons of bicarb in each of these, and then we've got our vinegar going slowly reducing. And you can see that with the launch time, as we reduced the vinegar, the time took longer to launch, except for this strange one here. This is not what we would have expected, so that might require further testing. And then the height also dropped off, but then seemed to just plateau after a while. So the longer time and slightly less height with the less vinegar. Similar results in the next part of the experiment, where we kept the vinegar at 1 cup and reduced the bicarb down 1 teaspoon at a time. You can see that the time increases quite a lot over time when we've reduced that bicarb down, and the height drops off too, but stabilises and plateaus. So we can conclude that we can assume that the more ingredients, or the ratio that you have, the faster the reaction time and the height. Some of the challenges that we discovered in the testing phase was that the rocket stands weakened over repeated launches, so the stands need to be improved, and we could then consider maybe changing the angle to measure the height or the distance travelled in a different way. The folding method of the bicarb packets was really important, and the thickness of the tissue really affected the results, so that needs to be very consistent in order to get accurate results. And also the cork depth was really important as well. So if the cork was pushed in further, then this changed the results as well. So to improve this, a line or some way to guide that process so that that is a controlled variable would be a good improvement. So we're concluding that the more reactants you have, the faster the launch, but the optimal ratio needs to allow time for you to set and stand clear of the launch, without too long of a wait for the rocket exploding, but also getting an impressive height on the launch. The investigation would suggest that the optimal ratio for a 600 ml bottle could be 3/4 of a cup of vinegar with 4 teaspoons of bicarb, but we would probably need to do some further testing where we're controlling some of those other challenges to confirm that amount. So here are our syllabus outcomes. We've got working scientifically skills, material world, and design and production outcomes. So working scientifically will be addressed next. We are creating a testable question, and the children are thinking about how they will decide what is the optimal ratio of bicarb and vinegar to create this question, and then set their criteria, thinking about what they want to actually happen. They need to decide how to change the mixture to test the effect of these different combinations, and doing it in a fair test, and then discuss what they think will happen or predict. They will plan and conduct their test using fair testing, and this should be mostly student-led with the teacher facilitating, just to ensure that there is fair testing and consistency, and also consistency with the results table that everyone will use, so that we can use the averages of the results. The independent variable is the vinegar and the bicarb, depending on which one we're changing. And the opposite one is the control variable at that point. The dependent variable is the launch time and the height the rocket reaches, and the controlled variables are many, but the launch site, the launch pad, the rocket design, and the bicarb packet, as well as a few others that we discovered. Repetition is essential in order to create reliable results with this one. There are potentially other variables that can't be controlled, so the more it is repeated, the better the results will be. 3 times was done for this experiment, but more would be ideal. And to help with accuracy, it's good to have the landmarks or changing that launch angle, as we discussed, to measure distance. And also the time until launch measurement needs to be very accurately measured too, by starting and stopping at the same time. Students will process and analyse the data with this investigation by collecting all their data in the results table, and then this can be plotted on a bar graph, and they can discuss in groups what conclusions can be made from the results. The groups can then communicate whether they felt their results matched their predictions and present this back to the class, and then the class can reflect as a group what we can conclude from the investigation, or what we need to do next. So material world outcomes addressed states of matter and mixtures. The state of the material, so the relevant inquiry questions from the New South Wales Science and Technology K-6 syllabus. How can the state of materials be changed and manipulated? Investigate and compare the properties of solids, liquids and gases. So the investigation allows you to observe the 3 different states of matter, but it's got to focus on gases because it's demonstrating some of the properties of a gas that you can see in the experiment. So the indefinite shape or volume and pressure of gases can be seen when we have it in the bottle, and it takes on the shape of the bottle, and as more is produced, the pressure builds up and exerts a pressure on the cork, making it explode upwards like our rocket. So this is focusing on gases. It's also talking about combining materials. So here's our other inquiry question: combining materials creates mixtures or new substances. So in this case, we are creating a new substance as we react the bicarb, which is a base, and the vinegar, which is an acid, to create a chemical change, creating the new substance, particularly of note, the carbon dioxide that we create. And so the new substances will have different properties and physical states to the starting materials, which is what creates the explosive effect of our rocket. Our design and production outcomes are being met here with this extension activity. So we identified several problems with that we needed to resolve with our experiment, and one of which was the rocket stand. So the design and production can create a nice stable rocket stand. Doesn't have to look like this, but here's an example of a couple that you could create, and this could be done with other recycled materials, and they can use different things to cut up their materials or create different things, and also improve the aesthetic of the rocket as well. So that will give us a stable launch site, and we can incorporate into that an option to change the angle as well. We also want to increase the stability of our flight, so we might dress our rocket up with some stabilizers here that will both make it look nice and fly better. And then also it would be nice if our rocket could land safely, so we're going to design a parachute as well in order to do that, and how to incorporate the parachute into the rocket design as well. So we've got our need that we've identified. They're going to need to do some research and planning, where they'll draw a plan for their design, thinking about what the different materials are that they can use to achieve this purpose, and then create that and then test it. Again, using our similar experiment, but with our improved situation from our design and production. So the scientific concepts in this experiment are about chemical changes and the properties of gases. So when combining the bicarb and the vinegar, in this experiment, a chemical change occurs. We can talk about how this, a chemical change is irreversible and occurs when certain materials are combined that create new substances with properties different from the original substances. And we can note the difference to physical changes which are reversible and do not create new substances. Here's the chemical reaction that occurs when we're doing our bicarb and vinegar reaction. And you probably wouldn't show the children this whole molecular structure, but it does help to break down what's happening. So here's our bicarb, which is a base. It's in a solid form as a powder. Here's the acetic acid is the vinegar, and that's a diluted acetic acid, and that's a liquid. And when you put those two things together, they create these things: carbon dioxide, water, and sodium acetate, or like a salt. So we've got the gas, which is what we're most interested in, and the effects of bottling that up. And then you get water, and then the salt here dissolves quite easily into the water. Now, this is actually a two-step reaction to get to this end point here, which is probably a bit complicated for stage 3. But first, these two reactants react to form another salt, which then breaks down into the carbon dioxide and the sodium acetate, so to create the end result here. So we're also looking at the properties of gases in this experiment too. So we're containing this reaction in the bottle, and this is going to help us visualize the gases, which are sometimes hard to see. So we know we can learn about how gases have a low density. You can see in the picture here. And this allows the gas particles to move around quickly, and this is what helps it escape from the neck of the bottle very quickly, being a gas. There's also an indefinite shape or volume to gases, so they expand or contract to fit the shape of any container that's holding them, which happens inside our bottle, until so much gas is created and the pressure that's exerted by these gases on the container becomes so great that it pushes out the end of the cork and shoots up into the air, so demonstrating to us the pressure effect of the gas. So that's the end of the show. All 4 presentations, lots of fun to do. Thanks very much for listening.